Okay, part 2 of our class notes on estimating net area using a Riemann sum. Now, I had asked before we took the break for each group of people to either use a left endpoint, a right endpoint, or a midpoint to use for the height of your rectangles. So let's take a look over what would have happened for your left endpoints. Now, when we're taking a look at the left endpoints, what we're doing, first off, and this is the same for the left, the right, or the midpoint, we're going to look for the width of each rectangle, because area, of course, is width times height. So if we have 10 rectangles, which I have highlighted right here, so if I have 10 rectangles, then what I want to do is I want to calculate the width of each rectangle. Now, this is not something that is absolutely required, but this is, of course, assuming, I'm going to put this up here, assuming equal width. It does not necessarily have to be equal widths, but for a lot of the Riemann sums that we do, we definitely want to let them be equal because it would be easier for us to get an estimate. So if they tell me that we want 10 rectangles, so if I want 10 rectangles, then to calculate my width, and this is the formula that you do want to basically memorize. It's going to come up for some problems that we're going to do later on. But to calculate the width, you take the end of the interval minus the beginning and divide by the number of rectangles. So this is definitely a formula that you should memorize. So I calculated it for this situation with 10 rectangles, starting at 0 and going to 10 hours. So that gave us a width of 1 hour for each rectangle. Okay. And so it doesn't really matter. You'll notice that in all of the examples that I've shown you, we're going to have the same width for left, right, or the midpoint. Now remember that what we talked about before we broke is that the height of each rectangle comes from the function value. So we're going to do the left endpoints. Now notice that the left endpoints, the first one will be 0, then 1, 2, and so on, heading up until the last left endpoint for the 10th rectangle would be 9. So, and notice that you have 10 left endpoints because we have 10 rectangles. And so I calculate the function values in the chart for each of those. And then when we go to do area, remember that your area, so we have our delta x, which we've calculated, same for everybody. Our function values, we plug in the left endpoint of the first rectangle to get the first height. I calculate the area of that rectangle by doing my width times my height. We repeat that for all 10 rectangles. And then over here in C, what's our best guess for the distance that she rode during those 10 hours? Using the sum of the rectangle areas, our best guess for this left endpoint selection is going to be 285 miles. Notation-wise, we call this L sub 10, and this is what we call a left Riemann sum. Riemann was just a mathematician who worked with this, so that's named for him. Now, in terms of this one, when we sketched our picture up here for the left Riemann sum, we can see that there's a little extra area that's not being used here. I'll shade that in red. So there's a little area here, 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 and so on. So if I were to ask you if this left Riemann sum is an over or underestimate, hopefully you would clearly see that this is an underestimate. So we underestimate because there's more area under the curve not included in the rectangle areas. So that's kind of what was important about that. How can we get a better estimate? Remember that as we are doing calculus, that calculus includes a limiting process where we try to make it a better and better estimate by changing something and applying a limit. So our limit here is going to let the number of rectangles increase to infinity. So by doing that, we're going to take the limit, let's say as delta x goes to 0, because that would mean the same thing. If the number of rectangles goes to infinity, the width of each rectangle is going to go to 0. Of the sum from I equals 1 to n rectangles, of this height of the rectangle times the width of the rectangle. So height times width. This is equivalent to saying the limit as n goes to infinity of the sum I equals 1 to n. Same height, f of x sub I, and delta x, I might change that to b minus a over n using that formula from above. And remember that the x sub I is going to be either a left endpoint, right endpoint, or midpoint. In the example that we did here, we used a left endpoint. All right, so now let's take a look at those of you that did a right endpoint. So over here in this example, notice that now my endpoints, when I'm looking at them, for each rectangle, you're choosing the one on the right side. So the first rectangle would be 1, then 2, 3, and so on, heading up until we hit the 10th rectangle, whose right endpoint is 10. And so then when we go to calculate our areas, in this case, notice we start with f of 1 because that's the right endpoint. We run through the chart and then we add it up, and we see that our right endpoint is going to have an estimate of 385. Now, when we look at that, what we see is that it's too much. Each of these rectangles sticks up a little bit too much over here when we look at them. So there's too much area in this. So the right estimate is going to be an overestimate. Okay, so let me just highlight that so we have it. Rectangles stick up above, so we include more area. So the right Riemann sum is an overestimate of the net area. Now again, I'm not going to repeat this, but clearly when I do this discussion, everybody should have this down at the bottom of their page because the limit formulas are the same no matter which one I use. And that might be something to make a note about as we're talking about it. As n goes to infinity, and this is why it doesn't matter which endpoint I pick, the left endpoint, the right endpoint, and the midpoint are all going to collapse and be essentially the same as n goes to infinity. So that's why it really doesn't matter which one we pick. All right, now for those of you that did the midpoints, now obviously you had a little bit more work. I think that's unfair for you guys, a little bit more calculation. And I was okay with the calculator here, but notice your midpoints right in the middle of each interval in each rectangle. Those would be those. So the first one would be 0.5, the second one 1.5, and so on. And so we kind of add this one in. Now, when we added those up, and again, it took you a little bit extra, we start with the height of the first rectangle would be the height by plugging 0.5 into the function value. And then we calculate each of those and we multiply and get it. So but we're still doing the width, delta x, your height, f of xi, and then the area of each rectangle is your delta x times f of xi. We add those up, and we end up with a midpoint Riemann sum of 332.5. Now, in terms of this one, for your over and your under estimate, you really can't tell in this one. Because, like, if you look at this rectangle right here, this part right here sticks up, and there's too much. But this part right here is not included, so there's too little. Now, obviously, when I look at this, I could say that I think that a midpoint Riemann sum is a better estimate than the left or the right, but it's more difficult to determine whether you're actually an over or an under. So they're never going to actually ask you that on the AP test. They are going to ask you about the left and the right being over and under, but not necessarily the midpoint. Now, you may ask, why don't we just always do the midpoint sum? Now, if you take a look at the three that we looked at, this midpoint sum was harder to calculate. Okay, so let's just say harder to do the computations, harder to calculate. So if I had to choose to get an estimate, I may not choose to do that one. And in the end, let's remind ourselves what we just said here. As n goes to infinity, all of these points are going to collapse and be the same anyway. So why do I want to do a harder calculation in the beginning when I can just use one of the easier ones and then apply the limiting process and end up with a good estimate? Okay, so now let's summarize what we've talked about with these Riemann sums that we have, some important ideas. So I'm just going to zoom in here. And then when we're finished with this, you guys will complete the Check Your Understanding for homework. All right, so the first idea, and this is kind of not really Riemann sum, but in general, but I did want to add it in so that you don't get confused. The net area under the curve from A to B is equal to the total distance traveled, this has to do with your particle motion, only if your velocity curve is greater than 0 on the interval A to B. So all three examples that we've done here, since all of the velocity curves were positive, then that was the total distance traveled. That is not true when the velocity curve is below. So we'll look at examples of those later. All right, other important ideas that we have here is, let's start with number 1 here. So that was just a side one. Number 1, the net area from A to B can be estimated using a Riemann sum. And a Riemann sum is the sum of n rectangle areas. Okay. Now, when we decided to do that sum of n rectangles, a couple of important things that we want to remember from this. Delta x would be b minus a over n, is going to be the width of our rectangles if equal widths. The second thing that we want to do is that our f of x of I is going to be the height of our rectangles. And in that, we don't really care. We can use left endpoints, right endpoints, midpoints, or actually any point in the interval to get the height, because they will collapse together. Okay, so our net area then, when we say a Riemann sum, or the sum of the rectangle areas, we can use our summation notation. I equals 1 to n, the number of rectangles, of the height of the rectangle, f of xi, times the width of the rectangle, delta x, so height times width, and that is going to give us our approximation for the net area, right? Now, to turn this into the exact net area, instead of just an approximation, then what we're going to do is we are going to do a limiting process. So we want to add in the limit as, if we're going to do delta x goes to 0 of this sum, f of xi delta x, or it's going to equal the limit as n goes to infinity, the number of rectangles, sum I equals 1 to n, same f of xi, and delta x, I'm going to write that as the b minus a over n to get it in terms of n. All right, a couple of facts about the estimate that we did, that if our velocity curve, if v of t is increasing, then our estimate, I'm going to use the notation, the left estimate is an underestimate, and the right is an overestimate. However, if, we'll put a little star in front of that, v of t is decreasing, then the left is an overestimate, and the right is an underestimate. Okay, that's going to finish up part 2 of our estimations with Riemann sums video. Go ahead and try the Check Your Understanding below, and I'll put up a homework video for you to check your answers with that.